Hi everyone, this is Becky, and in this video we are going to look at, in a little bit more detail at Lewis structures, specifically at something called resonance and octet exceptions. So in class we've been talking about this idea of a Lewis structure, and we described it as our way of showing how atoms in a molecule are physically connected, right? So what's bonded to what? So our way of representing the structure of the molecule, and we said that this is two shared valence electrons, right? And if we have valence electrons that aren't shared, we draw them as a single line, and essentially we've been drawing these as kind of a connect the dots type thing. And Lewis structures are great, but there are some things that they're not so good at, and one of those things is this idea of an octet exception. So I want you to consider the BF3 molecule, boron trifluoride. So when you draw a Lewis structure for boron trifluoride, the first instinct is going to be to say, okay, well, I'm going to add my 3 fluorines right here, like so, and then here. But if I do that, then boron doesn't have an octet, right? So boron only has 6 electrons. So what we've done before, we take this unshared pair and we make it shared between the boron and the fluorine. And so we end up with something that looks like this, where we have a double bond between one of the fluorines, and we have our structure here. That's 2, where we have all of this here, and everything has an octet, and everything is yippee skippy hunky dory, right? There's a couple of problems with this structure. Number one being the nature of fluorine itself. So fluorine is the most electronegative element in the universe. So in this structure that we've drawn here, where we have fluorine with a double bond, we have taken electrons, the boron, something that's way less electronegative than fluorine, has taken electrons away from fluorine, which is the most electronegative element in the universe. Nothing can take away fluorine's electrons when it's bonding. It just can't, right? We cannot give fluorine, in this case, it has a positive charge. We can't just, no. Fluorine will never double bond. Fluorine never double bonds. Okay, so if fluorine can't double bond, the only possibility for this structure that includes the right number of electrons is going to be the one that we first drew up here, where we have it like this, where boron does not have an octet. And it turns out that that's the actual structure. So this is the structure of BF3. Boron is what we call an octet exception, in that it's an atom that is stable with less, in this case 6, or more than 8 valence electrons. The most common octet exception that we've already seen a ton of is hydrogen, which only has 2. In fact, it's so common we don't even consider it really to be an octet exception. But boron is one that's perfectly stable with 6, and that's really the only octet exception that we talk about. There are others. So for example, every element that's in period 3 and below can have expanded octets. So they can have more than 8 valence electrons. And that's just something you should be aware of. It's not going to be our main focus. The one octet exception other than hydrogen that we would ask you to remember is boron. So boron doesn't have an octet. It has 6 valence electrons. The other place where Lewis structures are a little bit weird is in dealing with something called resonance. So to help us illustrate what this looks like, let's consider the NO3, the nitrate anion. So when we draw a Lewis structure for nitrate, right, the nitrogen is in the middle, we have an oxygen, 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 and then we end up having to double bond the nitrogen to one of the oxygens in order to give everything an octet with the right number of electrons. We put it in brackets because it's an ion with a negative sign on the outside. Okay, so let's look at this structure in a little bit more detail. Okay, if this structure, the one that we drew right here, is the actual structure for nitrate, when we look at it, what we should see are 2 different types of bonds. Right? If this were the actual thing, if this were what nitrate actually looks like, right? Some of the NO bonds would be single, so they'd be longer and they'd be weaker than the other NO bonds, which would be shorter and stronger. Right, so if I look at the bonding, if this structure actually represents the bonding that's in nitrate, when I look at the molecule, when I do a crystal structure and I look at the distance between the bond lengths of the nitrogen and oxygen, I should see two different bond lengths. But when I look at the structure, when I examine the structure and I examine the bond lengths of nitrogen, of the nitrogen-oxygen bond, all of these are identical. They're all the same, and they're all shorter than a single, but longer than a double bond. Okay, so how can we explain this, right? Let's take a more detailed look at the structure. So if I have my nitrate here, this is the same one that I just drew on the other slide. I just needed a little bit more room. Okay, so there's my nitrate molecule, my nitrate ion here. And in order to explain how the fact that these bonds are identical, what if I take this double bond that's here between these guys and I move it here? All right, I get a structure that looks something like this, where I have the nitrogen, and now I put the double bond between that oxygen, nitrogen and that oxygen, and then it looks like that, right? And I can take it a step further and then put the double bond here between the other nitrogen and oxygen, so over here. Okay, now, just like that, that's an oxygen. Okay, so taken alone, none of these structures adequately represent the bonding that's in nitrate, because all of these structures that we've just drawn isolate that double bond. And the double bond, those electrons that make up the double bond, can't be isolated. If they were isolated, then it would be a pure double bond. And we know that it's not, right? It's a partial double bond because they're all identical. So these electrons that make up this double bond are what are delocalized. Right? They are free to move throughout this structure. Just like in metals, when the valence electrons are delocalized, in this case, they're delocalized within this nitrate unit, so within a smaller space. And when we have that, when we have electrons that are delocalized within a molecule, that molecule has what is called resonance. Okay, resonance is this idea of delocalized valence electrons. And resonance imparts some very special properties to a molecule that you'll learn later in organic chemistry. And it's very special, very stable, leads to very stable structure. But you'll learn more about that in organic chemistry. Right now, what we want you to be able to do is to be able to recognize when resonance occurs. And resonance is going to occur when you can move the double bond around without changing anything else. So in this case, I can move that double bond. I haven't changed anything else. I've just moved it around between the nitrogen and oxygen. They're all identical, haven't changed anything. That's resonance, okay? Taken alone, none of these structures adequately represents the bonding that's present in nitrate. But when we take all of the structures that we've drawn here, so all of these, and we kind of superimpose them on each other, that somewhat represents it a little bit. Not a lot, but a little bit. So when we do that, we get something called a resonance hybrid, which in the case of nitrate would look something like this. You have the nitrogen, a pure single bond between all of the oxygens. Each oxygen is carrying two lone pairs, and then you have this partial double bond between all of the oxygens, and this whole thing is carrying a 1- charge. This is called a resonance hybrid, just for funsies. And it's our best way that we have of representing what the bonding actually looks like. We're not going to ask you to be able to draw that. All we're going to ask you to be able to do is recognize when a structure has resonance. Okay, and so another example Another example of a structure that has resonance is the carbonate anion. So if we look at carbonate with its CO3 2- charge, all right, so carbon is going to be our central atom because it's less electronegative. So I have a carbon in the middle. I'm going to bond it to 3 oxygens here. And then one of the oxygens is going to have a double bond to the carbon, and then there's 3 lone pairs on the other 2, and it looks something like this. All right, so this looks remarkably similar to the nitrate ion in that I have this double bond that I can move to be between this oxygen and that carbon. All right, and I get a structure that looks like this. All right, and I can put it between the oxygen and this carbon here, and I get a structure that looks like this. Oops, that's a single bond. Here, right? So this structure, again, has resonance, right? And like I said, resonance imports some special properties to the molecule, which you'll learn about later in organic chemistry. Now, if you remember, we also talked about we also know a different ion that looks remarkably similar to the carbonate ion. That is the bicarbonate ion, which is HCO3 with a -1 charge. We'd like you to think about that bicarbonate ion. Resonance implications of bicarbonate are different than that of carbonate. We want you to draw a Lewis structure for bicarbonate, and then any applicable resonance form. So if there's a resonance form for bicarbonate, draw the resonance form. Okay? Bring your answer with you to class next time, and we'll see you in class.